In this session, I'm going to prove the distributive property for the cross product. Where A, B and C are all vectors. So here, I start from the definition of the cross product. Let me start by sketching out the definition for A cross B and for A cross C. Okay. So suppose that this is the vector A and this is the vector B. Now this is supposed to be in 3D, so the cross product would be perpendicular to both of these vectors. It's a bit hard to imagine, but let me try anyway. Say that's A cross B. Okay, so this is at the same time perpendicular to B and perpendicular to A. And if this angle, let me call this angle beta. If this angle is beta, then the length of A cross B is AB sine beta. Next, I shall try and sketch the definition of A cross C. So suppose that this is A again, the same A as that. And now suppose that C is this vector. Then A cross C must be perpendicular to both vectors. Okay, so this is perpendicular to this and perpendicular to that. That's supposed to be in 3D as well. And if this angle in between A and C is gamma, then the length of this vector should be AC sine gamma. Okay. Now, while we are here, you remember from the last session, this length, this magnitude is actually equal to the area of this parallelogram formed by AC. Alright, simply because if you think of A as the base, then C sine gamma, C times sine gamma, is just the height. If I drop a perpendicular to here, this is C sine gamma. And let me call this height, say, I'll call it H. Right, and likewise, I can think about a parallelogram here. Then this length is equal to the area of the parallelogram because A is the base and B sine beta, perpendicular from here to here, is the height of this parallelogram. Let me call this height K. Okay. So we have a visual description of each of these terms on the right of the law that we want to prove. And in the next step, I shall turn to the left hand side and think about a corresponding picture for that. Let's first start by thinking of B plus C. Now, B plus C is here, is this B plus this C there. So let me try and sketch that. If I have B here and I have C from there. If I want to add B to C, I can draw a triangle of addition. That gives A plus C, B plus C. This would be B plus C. Okay, this would be this. If you now do A cross B plus C, I can sketch the definition for that. Like before, I can think about this vector A. Alright. Then the A cross of A plus B, A plus C, sorry, A cross of B plus C, this cross this, must be perpendicular to both of these vectors. So let's say, right, let's say it is here, in this direction. A cross B plus C. Alright, where this is perpendicular both to B plus C and to A. And as before, the magnitude of the cross product should be equal to the area of this parallelogram. Now, if I call this angle theta, Then, as before, I can think about the area of the parallelogram as the base times this height here. And I shall call this, so I call that K, I call that H, I call that K. Let me call this L then. So far so good. I have a separate picture for each of these. Now clearly the next step would be to somehow combine these pictures and ideas so as to prove that this is actually equal to that plus that, which is what this is saying, right? So this is that one, this is that one, and this is that one. Okay, so the aim now is to show that this vector plus that vector must somehow be equal to this vector. And I shall try and do it using these pictures that I have sketched. So now let me draw a fresh picture combining all the three pictures that I have drawn. That is A, vector A, that is the vector B plus C. Okay. Now, this is the vector B. Now I can, and this is the vector C. Remember that this is a three-dimensional picture, so they're not all in the same plane. Now let me complete the parallelograms. So parallelogram with A and B as the sides would look like this. That. The parallelogram with A and C as the sides. Right, I'm now going to, instead of this as the A, I'm going to think about shifting the vector A to there. Right, that's the same as A. So now the parallelogram between A and C would be this one. Okay, so that's A as well. And the parallelogram between A and B plus C would be this one. So this is the remaining side. So I have what looks like a prism. Okay, so this is a 3D picture that is that has the shape of a prism with 3 sides and the 2 ends. So I know that I have these angles here. This is the angle, this was the angle beta, that was the angle gamma. Right. Now, let me think about the height of each of these 3 parallelograms. If I drop a perpendicular from there to there, just somewhere from some point along this vector A, drop a perpendicular to here, the length of this side will be the height, k that I drew just now. So this is k, and if I drop a perpendicular from there to there for the height of this parallelogram, that's not very clear as it is. So that is the height. So okay, I'm obviously drawing it almost perpendicular to this, as if it's a 2D picture, which it shouldn't be. So let me change that a little bit. Let's say this is somewhere along here. Okay. So let's say that's the height h. Okay. And then I have a corresponding height here, which is L. Wait, so this is supposed to be making a right angle with this side. Then let me draw the height for this parallelogram. So that's a right angle as well. And I have called that L. Now we see that the 3 perpendiculars join up because this is simply the cross section that we would get if we cut this prism perpendicular to any of its sides. Okay, but note that this triangle is perpendicular to all the edges, so it is actually different from this triangle at one end of the prism. Okay, so these are not the same triangles. Okay, now I'm now going to think about the 3 cross products, that one, and this one. So this cross product, A cross B, right, A cross B is perpendicular to this plane, this parallelogram. So it would also be perpendicular to K. So let me just take out this part of the triangle. Lots of colors here to use. Let me take this out and just put it onto a 2D piece of paper. Right, so that is the L, which I'm just going to draw this horizontally. That's the L. That's the K. And that is the H. Okay, 3 colors. That's the triangle of this cross section. Now, so I was talking about A cross B. And A cross B, if you look at this, is perpendicular to this side of the figure, this plane contained by A and B. So that also means that it is perpendicular to K, and it's also in the same plane as this triangle. Right. So on this 2D piece of paper now, I can think about this A cross B as having this direction. Alright, and likewise, we have the corresponding cross products for each of these sides. As for the H, if we go back to this, A cross C is perpendicular to A and C, to the plane containing A and C, this and this. So it must be perpendicular to H, and it must lie in the plane contained by this triangle. Let me sketch it out here. A cross C. And likewise, A cross B plus C. A cross B plus C is perpendicular to this big parallelogram, which is here, and so it must be perpendicular to this side L, and it must lie also in the plane of this triangle, since the triangle is perpendicular to the plane. So, and I can sketch that here. A cross B plus C. Right. Now the next thing that I need to do is to think about the lengths of each of these vectors in terms of the sides K, H, and L. Let me start with A times B. So going back to the first figure, A cross B, see that the length of A cross B is AB sine beta. And as I've mentioned, the B sine beta is the height of this parallelogram K. So this is just A times K. Okay, let me write it down here. So the length of this is A times K. And likewise, for A cross C, if we look back at the second figure, see that C sine gamma, C sine gamma is the height of this parallelogram. So base times height, that makes sense. Okay. Alright, so that means that the magnitude of A cross C is A times H. It's just the area of the parallelogram. So this is A times H. That's the length of this. And likewise, for the length of this vector, oh, I've drawn it the wrong way around, haven't I? Oh well. So actually, that's not the right way. It should be the other way. Right. So the length magnitude of this vector would be the area of this parallelogram, which is A, the base, times L, the height. So this would be A, L. So now let's look at these lengths of the three vectors. Notice that I have AK, AL, AH. Alright, each of this vector has a length that is equal to the same number A times the corresponding site. See, for the site K, this vector is AK. The site L, length of the vector is AL. Site H, length of the vector is AH. And remember that all three vectors are perpendicular to the corresponding sites. Now, what I'm going to do is I'm going to rotate each of this vector by 90 degrees. Let's say clockwise. If I rotate AL by 90 degrees, it will lie along the direction of L. Right, that's AL. I just rotate that, and if I rotate AK by 90 degrees, it will lie along the direction of K. And if I rotate AC by 90 degrees clockwise, it will lie along H. Now I have drawn it as a closed triangle. But the question is, should these three sides, should these three vectors form a closed triangle? Well, it should form a closed triangle because this triangle is similar to this triangle, simply because the corresponding sides have the same ratio, which is A. Alright, each of these sides is just A times the corresponding side. Therefore, they form a closed triangle. And if they form a closed triangle, now let me rotate it. Take this and rotate it back towards 90 degrees. Right, if I rotate this back 90 degrees, those arrows will be pointing in the directions of the vectors of each of these cross products. Okay, running out of pen. Let me draw that properly. So let's see. The AL, if I rotate it back like that by 90 degrees, okay, wait, I want black color. That would be the A cross B plus C. For AK, if I rotate it back 90 degrees, that would be the A cross B. Right. AH, if I rotate it back 90 degrees, it would be A cross C. Notice that we now have a vector triangle. Vector triangle like this. And clearly, this vector plus this vector is equal to that vector. Let me write that out. A cross B plus A cross C, according to this vector triangle, is equal to A cross B plus C. And that is nothing but the distributive law that I wanted to prove. So this completes the proof. We'll stop here.